Hey, Super Chemists. Welcome back to Unit 8 lecture. This is video number 2. Okay, and I'm going to start with this in your notes. So when we talked about solubility rules, I gave you a pretty colored piece of paper that had this exact thing on it. And the reason I did that is I don't expect you to memorize these, but I do expect you to be able to use the solubility rules table. And I told you in class if you kept that pretty colored cardstock thingy-mabob that I gave you, that you could use that on your test for this unit. Now, most people thought this was pretty easy. You just had to read and kind of see if the solution or the compound you were looking at is soluble in water or not. So using this, we did a couple of examples just to make sure we understood reading the table. And we found out that potassium chloride is soluble in water. Because if you look at that table, it says everything that has potassium in it is soluble. We found out that barium sulfate is not soluble in water, because if you looked at it, it said all sulfates are soluble unless they're hooked up with, and one of the exceptions was barium. Okay, we found out that silver chloride is not soluble. Most chlorines are soluble unless they are hooked up with silver. We found that potassium hydroxide is soluble and sodium nitrate was soluble. And again, all we did was read the table. It wasn't too crazy, Pooh. Now, the next slide that we're going to look at says precipitation reactions. And those are really cool because you take a liquid and another liquid and you mix them together and bam, you have chemistry magic. You've made a solid. And it actually looks like it's snowing or there's a little precipitate falling out of the solution, and that's why they're called precipitation reactions. Now, because you are a super duper chemist, I'm going to expect you to take two solutions or two compounds, figure out what they produce, and figure out if anything you produce is not going to dissolve in water and is going to look like a solid. So the first thing we want to do is figure out how we're going to do this equation. How do we figure out what we're producing? I think it's easiest if you just circle or put a box around your metals or your positive charges or the first thing there, and they're going to switch partners. And what that means is that this potassium is going to switch partners and it's going to hook up with that nitrate. Now, because I am a super chemist and I remember my charges, okay, potassium is in the first column, so I know it takes a charge of +1. I know that nitrate takes a charge of -1 because I have memorized my polyatomic ions, okay? If something takes a +1 charge and a -1 charge, that equals 0. So potassium nitrate is going to look like that, okay? Now, my lead has to hook up with my iodine. Now, I know that iodine takes a charge of -1. I know that because everything in that column takes a charge of -1 on the periodic table. Because when I look at the periodic table on the noble gas side, there's 0. It goes -1, -2, -3. I don't know what charge that lead is taking, so I'm going to have to cheat and do what we used to call super chemist quick over here. Now, I know that nitrate is -1 and that there's 2 of them. So that means all of that is -2. If all of that is -2, that means that lead has to be taking a +2 charge to balance it. So I'm going to steal that information and take it over here. All right, so I have a +2 and a -1. They don't equal 0. So now I have to throw up my gain sign. Okay, so this compound is going to look like that. So now I've figured out what I'm producing. The next thing I'm going to do is balance my equation, okay? So I have 1K, 1K, 1 PB, 1 PB, 1 I, 2 I's. Ooh, I'm going to need a 2 here. That means I have 2 Ks, 2 nitrate, 2 nitrates, 2 nitrates, unbalanced, all right? So now I have a balanced equation. I want to figure out if either of these is going to be insoluble. Either of those are going to make a precipitation reaction for me. So I look at this. And when I'm looking at this, I notice that on this sheet right there, I want to make sure I point to the right thing, iodine tends to be very soluble, except when it's hooked up with things like lead. So this is going to be a solid. And whatever the solid is, I draw an arrow going down. That communicates to other superchemists that it is falling out of solution. It is precipitating. Okay? There we go. Next example, we're going to do one more so we can make sure we understand this. So I put a little box around metals, okay? They're going to switch places. So sodium is going to hook up with sulfate. Sodium and sulfate. Sodium takes a +1 charge because it is in the first column of the periodic table. That's going to be -2. That doesn't equal 0, so I crisscross, do my little gang sign. So that's what that looks like. And then I can have lithium hooking up with nitrate. Lithium and nitrate. Lithium gets a charge of +1 because it's in the first column. Nitrate is -1. They balance out. Now I'm looking at everything. I need to balance my equation. 1 sodium, 2 sodiums. 2 nitrates, 1 nitrate. So I put a 2 there. 2 lithiums, 1 sulfate, 1 sulfate. Now this one was tricky because if you look at this, okay, neither one of these are insoluble. Both of these are going to stay in solution, so you're not going to have a pretty precipitation reaction. We tend to put NR, kind of no reaction or no precipitate there, okay? That just tells me I'm not going to make any solid this time. Sometimes you mix 2 liquids and you end up with all liquid. Sometimes you can mix 2 liquids and you might get a solid there, okay? But it doesn't happen every time. The next part of your notes dealt with net ionic equation. And I'm going to erase the board before I start talking to you about that because you know we're going to need a little space. But it was fairly easy. It may have been a little tedious in class, but it wasn't, I didn't think it was too crazy poo. It just required you to remember some charges. Okay. And so the example from your notes is the example that I'm going to put up on the board right now. And in this example, I actually told you who was going to be the solid. Now you'll notice when you do this on your calculation sheet, I don't do that. I was just trying to be nice in class, okay? So I have this. I'm going to write a full ionic equation. And what that means is that every compound that is not a solid that's in that water that's broken apart is going to be written into its ions. So for instance, there's 3 of these. I know that the charge on strontium is +2. The reason I know that is because it's in the second column. Plus 3 times 2 is 6 chlorines. The charge on chlorine is -1. 2 times 3, 6 lithiums. Its charge is +1 because it's in the first column. 2 phosphates. Phosphate's charge is -3 because it's one of my polyatomic ions and I have them memorized. Now, whatever is the solid is not breaking into its ions because when we do the lab in class, you're going to see it stays all together as a solid. So anything that is a solid, we do not break down. So I'm just going to write that like that, and then I'll go to that. So everything that's not a solid gets broken apart into its ions, and the solid stays together. That's called the ionic equation. The next thing we're going to write is called the net ionic equation. Anything that's on both sides of the arrow that's exactly the same, you can cancel out. Just like in math class, if you have the same thing on both sides of the equal sign, you cross it out. So I have 6 chlorines here. I have 6 chlorines there. They cancel. I have 6 lithiums here, 6 lithiums there. They cancel. Nothing else on both sides of the equation looks the same. Whatever is left gets written down here. And this is called the net ionic equation. Okay? Now there's one more thing I showed you in class, and those were spectator ions. Spectator ions are just there hanging out. They're not doing too much. That's why they're called spectators. Anything you crossed out up here is considered a spectator ion. So up there I crossed out fluorine and I crossed out lithium. In class, I got a lot of questions about, well, why didn't you put the 6 in front of those? I mean, you can do that, but I'm not asking you how many or what quantity I have. I'm just saying, hey, these are the 2 substances. I'm just identifying the species, okay? So that was net ionic equations. Again, not tough, a little tedious, and it required you to remember a lot of your charges, okay? The next thing we talked about is, how does solubility really work? And the general rule in solubility is polar dissolves polar and nonpolar dissolves nonpolar. And we talked about polar and nonpolar when we did Lewis dot structures in the fall of the year, okay? If you do a Lewis dot structure and it's totally symmetrical, it has the same thing coming out all the way around the central atom, it is nonpolar. If you have a Lewis dot structure that is not totally symmetrical, it might have some lone pair dots here, might have something else hanging off here, that's polar. If you're polar, you can only dissolve other polar things. Water is polar, so it dissolves all polar stuff, okay? There we go. Now, we also talked about Henry's law. Henry's law was that thing, after a long, hard day of work, I go home and crack open a frosty cold ginger ale, okay? And it is delicious and refreshing. Why does it make that sound when I open that can? And well, everybody said, well, because it's got gas in it, it's got gas pressure. That's right. Well, how does that gas stay in my soda until I decide to drink it? Because remember, if I go take a sip and put my soda down and I come back 30 minutes later, my soda is flat. And the reason that that gas stays in that liquid is because there is a little liquid pressure inside that can that is pushing that gas into that liquid. And when you open that can, you are releasing that pressure. So there's nothing holding that gas into that liquid anymore, which is why my soda goes flat after a while when it's been out. The next thing we talked about in class were solubility curves, okay? We looked at solubility curves. We did some examples. You guys felt like these were pretty easy. This was like reading a graph. We have temperature on the x-axis and solubility on the y-axis, and I was just asking you to plot some points. The higher you are up, the higher your solubility. And the trend we see a lot is that solubility generally, but not always, increases when you increase temperature. And that's why when I make sweet tea, I make sure my water's hot, because if my water's not hot, then I can't get that sugar to stay in my tea. We talked about colligative properties. We did some calculations with these when we made ice cream. And we did talk about the difference between colloids and suspensions. And we said that colloids were homogeneous and suspensions were heterogeneous. And we talked about getting medicine from the pharmacy and having to shake it up because it was a heterogeneous mixture. I hope this helped you, and I'll see you in class. Bye, guys.